Welcome back. In the last class, we saw trigger generator circuits and first positive trigger circuit, negative trigger circuit, then positive and negative trigger circuit. Okay, and the key point here is whatever voltage we have here, if there is no trigger is there only when there is a transition in the input signal. Okay, after trigger, the output voltage at this node V0 dash of t is becoming 0. That is expected. Then whenever trigger comes, therefore it is going and then becoming 0. This is what is becoming 0. Actually, whenever you want to apply a trigger on top of a node voltage, which is what is driven by some other circuit, then if you want to apply trigger, only whenever you want to apply trigger, that time the trigger should come. Remaining time that node voltage from your trigger circuit should be floating, because that node voltage will be driven by some other circuitry. That is what your primary circuit. Then whenever you want to apply trigger, then only your circuit should come and then change the node voltage. Remaining cases, the node from your trigger circuit should be floating. That's why PN junction diode has come into picture. Therefore, if this is 0 and if it is positive voltage or whatever it may be, right, this will be always in reverse bias. Always the PN junction diode should be reverse bias. Okay, that is what it is. That's why here also we have taken positive PN junction diode and the negative PN junction diode. Therefore, only when triggers come, then only your output will be changed, else your output will be floating. Okay, that voltage will be driven by some other local circuit. That is what I am going to explain now. Case 2, monostable multivibrator. Okay, let's see the circuit and how it is different from the stable multivibrator. Okay, now just diode is added. Okay, let's see. And this is what is your beta V0. And initially voltage across the capacitor is 0. Okay, let us say this is what is 0 volt at a time t is equal to 0. Okay, now you can start. Let us say your output, because is it positive feedback or negative feedback? I already told you this is nothing but positive feedback. If it is a positive feedback, it is a comparator. Therefore, it is comparator. It is comparator circuit. Okay, now let me explain whatever we had seen. Okay, now we need 3 waveforms, whatever it may be. This is what is time t, and now this is nothing but voltage across the capacitor. Initially the voltage across the capacitor is 0. Then in between I'll explain something. This is what is time t, and this is what is our output voltage. This is what is our output voltage. I'll explain what is this. Okay, now let's see what is voltage across the capacitor. 0 at a time t is equal to 0. Let us say your output voltage, this is what is having plus VCC, same as a stable multivibrator, but you know, let's see what's happening. Therefore, let us say VCC is equal to 10 volts, minus VCC is equal to minus 10 volts. Okay, then listen. Let us say initially the V0 is equal to VCC. When I say this is what is VCC, then what is our beta V0? Your beta V0 is equal to, let us say R1 is equal to 1 kilo ohm and R3 is also 1 kilo ohm. Then this is 5 volt at a time t is equal to 0. At a time t is equal to 0. Right? Therefore, now tell me, this is 5 volt at a time t is equal to 0, and this is what is 0 volt at a time t is equal to 0. Which is more? 5 is more or 0 is more? 5 is more. When 5 is more, your output is plus VCC, 10 volts. Therefore, what is your output? Your output is Your output is plus VCC, which is 10 volts. Let us say. Right? This is what is time t is equal to 0. Therefore, now tell me, your output is plus 10, right? Then there is a capacitor. Then the voltage across the capacitor is 0. Now, can I say your capacitor is trying to charge to what? Your capacitor is trying to charge to plus 10. Your capacitor is trying to charge to plus 10. When capacitor is trying to charge to, let us say this is what is your VCC. Your capacitor is trying to charge to plus 10. But remember, once the capacitor voltage charges to greater than or equal to V gamma, PN junction diode will come into picture. Actually, PN junction diode is the one which is what is limiting the voltage across the capacitor to do not cross the V gamma. Why? Once the PN junction diode or once the voltage across the capacitor is crossing V gamma, then PN junction diode will come into picture. It will be turned on. When this is what is turned on, then it will have voltage of V gamma and it will stay there only. Your capacitor cannot cross that, right? Therefore, when PN junction diode will be conducting, then it will act as a battery. When it is acting as a battery, then your capacitor voltage cannot cross because this is V gamma, it will be stuck to V gamma. Therefore, the voltage will be stuck to V gamma. This is what is your V gamma. Therefore, now what is voltage across the capacitor? It is at V gamma. When that is at V gamma, let us say this is at V gamma, your output is plus VCC. That's it. It is stable state. Therefore, when output is at 10 volts or when output is at VCC or logic 1, this is what is called stable state. Why it is becoming stable state? The PN junction diode is limiting the voltage across the capacitor to do not cross V gamma. To do not cross V gamma. Once the PN junction diode is conducting, whatever current which you are getting, earlier if PN junction diode is not there, your capacitor is charging through R, then whatever current you are getting, transient current or charging current. Now when PN junction diode is conducting, instead of flowing through capacitor, it will go through PN junction diode and then maintain always V gamma. Therefore, now whatever current which you are getting, that is what is flowing through PN junction diode. There is no current entering into capacitor. Capacitor charges to 0.7 and it stays there because current is not entering into capacitor. The current will be flowing through PN junction diode because parallel path which is coming to picture, your PN junction diode starts conducting, then the current will be flowing through PN junction diode, not through capacitor. Then the capacitor voltage will be stuck at V gamma. That is nothing but V gamma stable state. It is what is forcing the PN junction diode, is forcing the output state to stable state. Therefore, now this state is stable. Can I say this state is stable? Yes. Therefore, maximum it will go to V gamma. Therefore, this 0 volt will become what? It will go to 0.7 volt. Let us say at a time t is equal to t1. At a time t is equal to t1. Therefore, let us say this is what is time t is equal to t1. This is time t is equal to 0. That's it. Once it reaches V gamma, it stays there only. Therefore, now tell me, this is 0.7, this is 5, plus is always more than minus, always your output will be 10 volts. That's it, done. This is what your stable state. This is what your stable state. Nothing. Under steady state, your output voltage will be like this only. But I want to disturb the state. I want to disturb the state. Then we need to apply trigger. Where will you apply trigger? I want to disturb the state. Where will you apply the trigger to disturb the state? Simple. This is 0.7. Keep it like that. This is 5 volt. If we can pull momentarily, not continuously, okay? Momentarily, if I pull this 5 volt less than V gamma or less than 0.7, just momentarily like a trigger, negative trigger, then this will be pulled down less than 0.7, then minus is more than plus, let us say pulled to 0, then 0.7 and then 0, 0.7 is more than 0, then negative is more than positive, then output voltage will be, instead of plus 10, it will become minus 10. Therefore, your output state is disturbed from stable state to some other state. Okay. Now we need to apply trigger. How will you apply trigger? That's what I told. Therefore, this is what your C and then R. We want to apply negative trigger. Therefore, if I want to apply negative trigger, let us say this is what is the PN junction diode which I am applying here. Therefore, now whatever trigger you want to apply, you apply a square wave here, let us say. Then whatever trigger you want to apply, you apply. This is what is the trigger input. Trigger square wave. This is what is your trigger input. This is what is your trigger input. Therefore, we are going to get trigger. This is R, this is C. This is differentiator, but now this is what the time period of your trigger square wave, then trigger input. Let us say we are applying the trigger with respect to the trigger. This is what is time t is equal to 0. Therefore, we are applying trigger. Let us say the trigger voltage. Till then it is floating. Whenever you want to apply trigger, let us say I am applying trigger here. I am applying trigger here. Whenever trigger is applied, this is what is your time t, new time, whatever it may be. Therefore, it should be minimum or it should be 0. The trigger voltage should go to 0. Therefore, this is what is your trigger input. This is your trigger input. This is what is your trigger input. Therefore, now tell me, momentarily what will happen? This voltage will be triggered down. Therefore, when this is what is becoming 0, this is what is pulled down. Let us say that is what is time t2. This is what is time t2. At the time t2, trigger is applied. When time t2 trigger is applied, therefore tell me, then what will happen? This voltage will become, or this node voltage will become 0 volt, triggered down. Therefore, beta V0 will become 0. Beta VCC, this is what is nothing but beta VCC, right? Which is 5 volt. Beta VCC, it will become 0 at a time t is equal to t2. At a time t is equal to t2, right? But this is what is 0.7. This is 0.7 at a time t2 only. This is what your capacitor, right? Then what is your output? Therefore, once you apply trigger, negative trigger, once you apply negative trigger, then the beta V0, which is 5 volt, or beta VCC, which is what is 5 volt, that will become 0 momentarily at a time t2. Then what will happen? Your output voltage will become what? Your output voltage will become immediately, that V0 will become what? Minus VCC, which is minus 10, exactly at a time t2. Therefore, your output voltage will be triggered. Your output voltage is disturbed. Therefore, now tell me what is your output voltage? Your output voltage is minus VCC, which is minus 10 volts. Just listen, right? Therefore, now tell me what is your output voltage? Now your output voltage is minus 10. When output is minus 10, immediately, because this is what is triggered and then left, we have to leave it, right? Only whenever you want to change the state of the circuit, just to trigger it, pull it down to 0 and then leave it. Then when you pull it down to 0, immediately the output voltage will change from plus 10 to minus 10. When output is becoming minus 10, immediately the beta VCC, R2 divided by R1 plus R2 into minus 10, it will become minus 5 volt. Then it will become immediately this will become minus beta VCC. It will become minus beta VCC, minus 5 volt, just T2 plus. What do you mean by T2 plus? Just after time T2, the moment you apply the trigger at time T2, this is what is time T2. The moment you apply the trigger at a time T2, just T2 plus. After that immediately, because of output voltage when it is changing from plus 10 to minus 10, immediately this node voltage will become minus 5. Therefore, now tell me, when this is minus 5, that's what I am saying. When this is minus 5 and this voltage, we know that it is a differentiator, right? If there is no trigger, the voltage at this point is 0. This is 0 and this is minus 5. Your PN junction diode will be in reverse bias. Then your PN junction diode will be floating. Then PN junction diode is floating. The trigger circuit, whatever you have, it is not disturbing the node what you have here. That node voltage is driven by your output circuitry or R1 R2 combination. That is what we need. Whenever you want to apply trigger, then only the trigger circuit should come and then apply the node voltage or pull down the node voltage, then change the state of your output. In remaining cases, once the trigger is applied, once the state is changed, then whatever voltage you are getting, which is nothing but minus 5 volt, for that minus 5 volt, because of PN junction diode, your PN junction diode will be in reverse bias, then the circuit will be isolated from this node, then normal action by your monostable multi-vibrator circuit. I hope this is clear. Okay. Now let's see. Therefore, now it became minus 10 at a time t is equal to t2. When that is what is becoming minus 10, your capacitor is trying to charge to what? Your capacitor is trying to charge to minus 10. Now when this is what is trying to charge to minus 10, it is discharging 0.7, 0.6, 0.5, 0.4, 0.3, 0.2, 0.0, minus 1, minus 2, minus 3. PN junction will be in reverse bias. Once the voltage across the capacitor is negative, your PN junction will be reverse bias. That will not limit the negative state or other state. Then you know what will happen? Your capacitor is trying to charge to what? Your capacitor is trying to charge to minus VCC. It is trying to charge to minus VCC. Let us say this is what is our minus VCC. But once it crosses minus beta VCC, once it crosses minus beta VCC, which is minus 5 volt, then what will happen? Once it crosses I'm trying to charge to minus beta VCC, but once it crosses minus beta VCC, then tell me, again normal operation. Therefore now tell me, once it crosses, this is minus 5, but this is at 0.7. Now slowly it is decreasing. Let us say this is what is becoming minus 5, because this is what is minus 5, right? Let us say this is what is minus 5 at a time t is equal to t3. When this is what is becoming minus 5, then what will happen? This is at minus 5, then it is trying to charge to what? It is trying to charge to minus VCC, minus 10 volt, minus 5.1. When it is minus 5.1 and this is minus 5 and then minus 5.1. Minus 5 is more than minus 5.1. Then plus is more than minus. Your output will switch from what? Minus VCC to plus VCC, which is 10 volt at a time t3. Therefore, immediately this will become beta VCC, which is nothing but 5 volt at a time t3. Okay. Therefore, now once it crosses minus beta VCC, then your output voltage will switch from, again it will be stable, then not stable, therefore it went back. Now your output voltage is becoming what? Plus 10. Your capacitor is trying to charge to what? Your capacitor is trying to charge to plus 10. When it is trying to charge to plus 10, again when it is trying to cross, it is trying to charge, but when it crosses V gamma, it will stay there only. Therefore, the state will be stable unless you apply trigger now, right? Let us say, again I am applying trigger to change the stable state, because this is what is stable state. Once it reaches to 10, it is stable state. Remember, this is what is stable state. This is stable state. This is unstable state. This is unstable state. Unstable state. Therefore, how to get stable state to unstable state? Trigger. Trigger is applied. Trigger is applied. When trigger is applied, it became unstable state, and then again it got stable state. Again we need to apply trigger. We need to apply trigger to get unstable state. Therefore, initially it is in stable state. We applied a negative trigger. It became unstable state. Then it has its own trigger. Then again that unstable state became stable state. Again it came back to VCC, stable state. Now again we need to apply trigger. Now if you apply trigger, again that state will be changed. Whenever it is entering into stable state, apply trigger. If it is unstable state, no need to apply trigger. It comes automatically to stable state, right? But in the case of stable multivibrator, both the states are unstable. Stable state to unstable state, unstable state to stable state. Sorry. Both the states are unstable. Unstable state to unstable state. Logic 0 to logic 1. Logic 1 to logic 0. Logic 0 to logic 1. Both the states are unstable. Continuously it is toggling multiple times and vibrating between 1 to 0. Therefore multivibrator. Here also one of the states is stable. Then to disturb the stable state, apply trigger. It will enter into unstable state. No need to apply trigger because that is unstable state. That will become again stable state. Again we need to apply trigger. Unstable state. Then it will become stable state. Apply trigger. Unstable state to stable state. Therefore, when you apply trigger, it is in stable state. It will enter into unstable state. That is what it is. That's why this is what is called monostable multivibrator. Therefore, multiple times you have to apply trigger. Multiple times your output voltage also will be changing. Okay. That is what it is. Therefore, now when you apply trigger, let us say whenever trigger is applied, your output voltage will change. Again, whenever trigger applies, it starts charging. From that point onwards, it is trying to discharge. Again, it changes the state. Okay, this is what it is. Now if I take, this will be continued, okay. Therefore this is what is our stable state. This is stable, then trigger is applied. Again this is stable, trigger is applied whenever it is stable, but this is unstable. This point is unstable and this is also unstable. That's why it is triggered and then going back. Therefore these points are unstable points. That's why stable state, trigger is applied. Therefore trigger is applied exactly at this point. Therefore the negative trigger, this is what is our trigger. Therefore trigger is applied only in stable states. When it is unstable state, trigger is not applied, okay. Exactly at this point it is unstable, okay. This is unstable, that is fine. Take the timing diagram, okay. Therefore whenever trigger applies, the state will change from +10 to -10. Therefore this is what is associated to your trigger. This is what is associated to your trigger. Whenever trigger comes, then only your stable state will become unstable. Whenever trigger applies, this is what is very important, okay. This is trigger. This is also trigger. When I say unstable, surely it will go to stable state. Again it will, when I apply trigger, it will enter into unstable state. Write down the timing diagram, okay. Now we can calculate the time t, right? Let us say this is what is the time t. This is new time axis. Let me take. Just ignore the first half cycle, right? Now if I take, this is what your new time axis, t dash. Therefore t dash is 0. Now I want to calculate. Let us say this is what is the time t. T dash is equal to time capital T. Therefore, this is what is the time I'm calculating, because after this only your state is changing, right? Once this is what is unstable and then going into stable state, then only it is entering into stable state. Now we can apply a trigger again, one more negative trigger from this point onwards. Then you can apply trigger not to 0, negative voltage. Then you know what will happen? We can change the again state. Therefore, what is the minimum time period? Therefore, in this time when capacitor is entering into stable state, from stable state to unstable state, in this time if you apply trigger, therefore trigger is to what? Trigger is to change from 1 to 0, but already it is 0. When you apply trigger in this mode, it will be 0 only. Therefore, it will not have any impact. Therefore, in this time, even if you apply trigger, doesn't matter. Why? Let us say your capacitor voltage is at let us say -4 and all. Your output is 0. We are applying trigger to change from 1 to 0. But already output at 0. When output is at 0, when you apply trigger, doesn't matter because it is already at 0. Then only to change the stable state, once it is entering into stable state, you can apply trigger. Once it is entering into stable state, it is trying to go from unstable to stable state. When it is trying to enter into stable state, now you can apply trigger to change from stable state to unstable state. Okay. Therefore, this is what is the minimum time period. After that only if you apply trigger, negative trigger, it will have impact, else it will not have any impact. Okay. In this scenario, I have taken this is what is 0 volt. But if you want to apply trigger here, wherever you want, whenever it is entering into stable state or entering into stable state, right? Then remember we have to pull it to negative voltage, which is less than minus beta VCC. Therefore, I can say instead of 0 volt, I can say this is what is minus beta VCC. We have to pull it to minus beta VCC. If you pull it to minus beta VCC, then we can change the state, the stable state we can change whenever trigger apply. But when it is an unstable state, remember even if you apply trigger, doesn't matter. In this state, even though you apply trigger, doesn't matter. The trigger pulse will be missed. Only when it is entered into stable state, then only if you apply trigger, whenever you apply trigger, which is to minus beta VCC, then it will have impact and it will change stable state to unstable state. Okay. This is only the minimum time period of trigger pulse. It is to know the minimum time period of your trigger square wave. Okay. More than that you can have, that is minimum time period. More than that you can have, whenever you have trigger pulse, it will change the state, the stable state to unstable state. That is what it is. Let's calculate how to calculate the time t. Again, voltage across the capacitor. What is initial voltage? V gamma. Final voltage minus VCC. But at time t is equal minus beta VCC, it will go to t. That is what it is. Okay. Let's see. Is this over? You take it. Then we will derive. We will derive what is capital time t. With this I can say monostable multivibrator is also over. Then I will explain qualitatively. Then that time I will not derive anything. Then because the same thing will be coming into picture. Therefore, now we will see astable multivibrator after this. Okay, take it. With that I can say multivibrators are over. The derivation part. Okay. Now tell me, what is voltage across the capacitor? From the waveform, right? We know that voltage across the capacitor is equal to V final plus V initial minus V final into e to the power of minus t by tau. Right? Therefore now I am speaking with respect to the time. 0 less than or equal to t dash less than or equal to t. In this time, what is initial voltage? Therefore, tell me with respect to time, what is initial voltage? V gamma. V gamma. Then what is final voltage? Let us say the final voltage is nothing but minus VCC. That is what it is trying to charge. It is trying to charge to minus VCC. Right? Now, if you substitute what is voltage across the capacitor, VC is equal to V final plus V initial, V gamma minus V final divided by e to the power of minus t by tau. Tau is nothing but R into C, right? Therefore minus VCC, V final plus V initial minus P final into e to the power minus T by tau. Okay. Then tell me at new time T dash, right? Therefore at a time T dash is equal to T, what is voltage across the capacitor? Voltage across the capacitor is equal to minus beta VCC, minus beta VCC. Therefore if you substitute, what you'll get? You'll get minus beta VCC is equal to minus VCC plus V gamma minus VCC into e to the power of minus T by RC. Then VCC will be cancelled and divided by VCC everywhere. Then minus beta is equal to minus 1 plus V gamma by VCC minus 1 into e to the power of minus T by RC. Right? Maybe you can take this minus 1 here, then 1 minus beta, therefore, or you can take anything is fine. Therefore, V gamma divided by VCC minus 1 into e to the power of minus T by RC is equal to, keeping this as it is, then if I take this side, this will become 1 minus beta. Then what is this? This will be minus T by RC is equal to, right, 1 minus beta divided by anything is wrong, V final plus V initial minus V final into e to the power of minus T by tau, right? Yes. Can anyone, because you didn't write it is fine. Okay, now you got the procedure right. Can you derive and then tell me what is T? Because you understood the procedure, right? I did one mistake wantedly. Okay, find it out. You know the procedure, right? VC is equal to V final plus V initial minus V final into e to the power of minus T by tau. Okay, you substitute and then tell me, you know the procedure, same thing, and then tell me where is that. Okay, procedure is a common, then you tell me. Okay, done. Okay, V initial is nothing but V gamma, V final is minus beta VCC, right? Therefore minus beta VCC minus VCC plus V gamma minus VCC e to the power minus T by RC. Okay, now minus beta minus 1 plus V gamma by VCC minus 1, right, e to the power of minus T by RC. Therefore, now V gamma by VCC, is there anything wrong? I will tell you. Okay, maybe if you do the what you call quantitative analysis, that is fine, but what is that I'll explain. Therefore, V gamma by VCC minus 1 into e to the power of minus T by RC is equal to, I can say 1 minus beta, then e to the power of T by RC if you take, then 1 minus beta by V gamma by VCC minus 1 V gamma by VCC minus 1. Then if you take to T, then T will be equal to R into C ln, right? This is ln of, okay? Then ln, because that minus if you take 1 by A is log A, therefore that is nothing but what? V gamma by VCC minus 1 divided by 1 minus beta. Why it is wrong, I will tell you. Can anyone tell where is the mistake? Can anyone think about it? Where is the mistake? See, mathematically everything is fine, right? Mathematically everything is fine. You're trying to find, what maybe you're trying to find this time, let us say, here to here. When you're trying to find, we are losing something. Because why it is having mistake, the reason to say why it is having mistake is, what is V gamma 0.7? Definitely less than 0.7. V gamma by VCC is nothing but definitely less than 0.7. Less than 0.7 minus 1. This is negative, but this is positive. Log negative is undefined. What is log negative? What is log minus 1? Do you have log negative value? Log negative value is undefined. But you are getting it. Then what does it mean? The time t is not defined? How did you find the mistake? Am I confusing you? Yes. Now I am getting log negative. What is log negative? Think about it. Okay? It is a homework for you. You have to tell me. Anyway, I'll explain the next session. You have to tell me. You have to tell me the issue what you have here. Okay? Thank you.